Welcome to the Titus Timeout podcast. My name is David Sanders, and today we're going to go over Part 2 of Acoustical Design Considerations for Terminal Units. In a previous installment of Titus Timeout, we went over how the source path receiver process can be used to outline a method of pathing out the individual routes sound takes from their point of origin to that of the perceiver. A table was created with the different variables within that process. Let's continue this discussion and look into how we can mathematically determine the overall sound levels in the critical paths. First, let's look at a source of the sound itself. To properly design, we have to know how much sound is being generated by the terminal. This is provided by the manufacturer. At Titus, you can find all of our acoustical data on our website for the most up-to-date information available. You will need the radiated discharge and outlet sound levels at their corresponding octave bands based on your design considerations. For this podcast, we will use these simulated manufacturer's data. Now let's start by looking at all of the attenuation that is present for each of the paths. Since path 1 has the least amount of variables, let's start there. One common attenuation is the environmental adjustment factor. While in indoor areas, rooms tend to be highly reverberant, which leads to less radiation of low frequency bands. We must adjust our source sound to accommodate this. This is a 2 dB reduction in the 125 Hz band and a single dB in the 250 Hz band. The only other attenuation of path 1 is the ceiling space effect. This attenuation is governed by section D1.6 in AHRI standard 885. These values were tested based on ASHRAE research project RP755 and hold true so long as the plenum is at least 3 feet deep, over 30 feet wide or insulated, and have no significant penetrations directly under the unit. For this example, we will assume that we are using a Type 1 mineral fiber ceiling. Now that we have all the factors for path 1, we can find the overall acoustical profile of path 1. We line the values of each of the octave bands up and do some simple arithmetic. Now let's move on to path 2. We add sound insertion attenuation and duct transmission loss factors for this particular path. This sound insertion attenuation is covered under D1.3.2 in standard 885. For this example, let's assume this is a 5 feet of lined rectangular duct with a cross section of 12 by 12 with 1 inch fiberglass liner. Please note that the values in this table are by the foot, so to find the overall you must multiply by the full length of the duct. The next variable is the duct transmission loss. This can be calculated using the geometry of the ductwork and an equation in section D1.2.4 of 885. You combine this data with the transmission loss table in D1.3 to calculate the duct transmission loss. The final attenuation of path 2 is the ceiling effect, which has already been discussed. As with path 1, the total acoustical profile of that path is determined by arithmetic. Moving on to path 3, another sound insertion attenuation is presented. This time we shall use 10 linear feet of duct. A new factor not previously discussed is the rectangular T. This type of attenuation is covered under D1.4.4, which is a factor of the width of the duct as it enters the T. Another new attenuation is the branch power division between the branches. This is covered under section D1.1 of 885. For this example, we are going to say that the division is a 50-50 split. The remaining points of attenuation in path 3 is another duct insertion loss, which we will use 5 feet on line rectangular duct, and another duct transmission loss factor in ceiling effect discussed earlier. The remaining 3 paths all follow the same procedure of starting with base noise generation provided by the manufacturer and applying individual attenuation factors identified in part 1, then use arithmetic to develop an overall acoustical profile of that individual path. Once we have all the paths' acoustical profile, a total profile based on the individual contributions can be generated using logarithmic addition for each of the respective paths. If we know where there are paths that generate the most unwanted noise, additional steps in the design or equipment selection can be taken in order to reduce the overall noise of any given space. This concludes our podcast on the source path receiver process. Don't forget to subscribe to our YouTube channel, and thanks for taking a time out with us.